Okay, so here's some review material. This is from way back when, but we're going to need this for today. The limit of sine h over h is 1. And I should add a little comment here. This is for h in radians. And it's the fact that it's in radians that this limit is 1. This is why we basically, after your first trigonometry class from calculus on, we always deal in radians. And it's because of this fact right here. And this is it. That's why you're subjected to learning radians. Okay, so we're going to need that for today. That wasn't what we did last time. What did we do last time? Well, we talked about the rules for derivatives. So remember that we did this a couple times ago. The derivative of a constant is 0. Derivative of x is 1. In general, if you have x to a power a, derivative of that is you bring the power in front, a, x to the a minus 1. So you subtract 1 from the power. If you have two functions added together and you want to take the derivative, you just take the derivative of each piece and add them up. If you want to scale by a constant, so you have a constant times a function. To take the derivative, you take the same constant times the derivative. We have the product rule, which is a very nice rule. And so you should memorize this rule because you can expect to see it somewhere. Derivative of f of x times g of x is f prime g plus f g prime. And this is a really important rule, which is why we would start this rule. Because this is going to be important when we go into the second half of the course, or probably more likely into 31b. Here's the quotient rule. Derivative of f of x over g of x, f prime g minus f g prime over g squared. This is not very well known and hard to remember sometimes. So the good news for you is I'm not going to test you on this. Or if I were to test you on it, I'd give it to you somewhere on the test. So you don't need to memorize the quotient rule. But make sure you memorize the product rule. I mean, if you remember only a few things from calculus when it comes to derivatives, this is a really important thing to remember. This is not so important. And there's one other thing that we didn't write down here, and that's because we haven't done it yet. The derivative of f of g of x, which we're still going to have to wait. This will be next week. Okay. Next week. Hence, after the midterm. So we don't need to worry about that right now. And in fact, everything we talk about today is after the midterm. It's only what we got up to last Friday. So some of the other things we talked about, marginal cost. This is an economics idea. The marginal cost is what does it cost to make that last unit, that last item? Well, it's fairly simple. You take the cost of producing essentially one more minus the current cost. And the thing to note is that this really looks like C of q plus 1 minus C of q. It looks like C of q plus 1 minus C of q over q plus 1 minus q. Because, of course, this is just 1. And this looks like the slope of a secant line, which, of course, is roughly the slope of a tangent line. So that's why the marginal cost, really the best way to think about it is a derivative. And when it comes to actually working with marginal cost, it's oftentimes much easier to work with the derivative. We also talked about higher order derivatives. For example, the second derivative, which we called f double prime of x. There's also this notation, d squared over dx squared. This basically means just the second derivative. And what is the second derivative? Well, very simple. You take the derivative of the first derivative. And just remember this notation here means take the derivative. So the second derivative is take the derivative of the first derivative. And we don't have to stop at second derivative. We can take third derivative, fourth derivative, fifth derivative. And in fact, we can take any kind of derivative we want. And so the notation for that, if I want to look at the nth derivative, where I start with the function, I take the derivative n times. The notation, there's two notations. Either f with the n in parenthesis. If it's not in parenthesis, it means something else. So the parenthesis there, almost always that refers to the derivative. So fn of x, or dn over dx to the n f of x. So these are both different notations for referring to the nth derivative. Now, why might we be interested in the second derivative? Well, the second derivative tells us how the first derivative is changing. Now, I guess I should use correct English here. Is, not are. Now, the first derivative tells us something about how the function is behaving. Because it tells us the slopes of the tangent lines. And we can look at it and we can know whether it's going up and going down. The second derivative, well, it tells us, again, something about the function. A little bit more subtle, it tells us how the slopes are behaving. So in particular, we saw that if the second derivative is positive, the slopes are doing something like this, where you see first we start off with a negative slope, and then it's increasing to 0, and then it's becoming positive. So here's an example of something where the second derivative is positive. Second derivative is negative. Well, it tells us that the curve is doing something like this, where we have positive slopes, it's decreasing to 0, and then it's becoming negative. Where the second derivative is 0, we don't know what's going on, so we'll just have this notation. And we're going to come back to this in a few weeks. Where does the second derivative show up? In motion, from physics. So we have the s of t is the position function, and I don't know why they use s, but let's just go with it. So if we know our position, there are some things we might want to know. We might want to know velocity. That's a function called v of t. Well, how are velocity and position related to one another? Well, velocities tell me how I'm changing in my position. If I want to know how I'm changing, I look at the derivative. So the velocity is the derivative of position. Another thing we might be interested in is in the acceleration. Now, acceleration tells me something about whether I'm getting faster, I'm getting slower. We call that a of t. And how's acceleration? Well, acceleration tells us how velocity is changing. So acceleration, of course, is the derivative of velocity. But we also know velocity is the derivative of position. So the derivative of the derivative of position is the second derivative of position. So the acceleration is the second derivative of position. So Galileo, he observed something. Hopefully I spelled Galileo right. Of course, that would be assuming I spelled it right here. Okay, so what did he observe? Well, he observed that if we look at things here on Earth, that acceleration essentially is constant. And he called it g. Well, I don't know if he called it g, but we call it g now. And, of course, we think of g as essentially gravity. And it's roughly 32 feet per second squared, or 9.8 meters per second squared. And these numbers, 32 and 9.8, they came from just taking measurements and experimentation. There's no universal reason why they're 32 and 9.8, at least not that I'm aware of. All right, so that's our acceleration. It's a constant. You said, okay, well, I know if my acceleration is a constant, maybe I can figure out what velocity looks like. And he thought about it for a while and said, okay, so what kind of function, if I take the derivative, gives me something that looks like a constant negative g? And he reasoned, well, if I have a constant, I'll call it v0, and I add to that negative gt. And he thought about it, and lo and behold, if you look, derivative of a constant is 0, and the derivative of negative gt is negative g. And he gave this v0 name. This is called the initial velocity. And said, okay, so now I know that velocity probably should behave like this. If I throw an object and I see how it falls here on Earth. Well, if I know velocity, I should just go one more step further and think about position. And he thought about it. He said, well, a constant, I can always have a constant in there, but that doesn't change anything, because when I take a derivative of a constant, it's 0. Well, what will give me a derivative of v0? Well, if I have v0t, that'll give me a derivative of v0. What will give me a derivative of negative gt? Well, you kind of think about how it goes. You know that the derivative of x to the a is ax to the a minus 1. You think about, okay, well, if I want to get an x on the right-hand side, that's like x to 2 minus 1. So I should really have something like an x squared, or in this case, a t squared. I said, well, wait a second, it's not going to quite work. What would happen if I had negative gt squared? If I took the derivative of that, I would get negative 2 gt. So I said, all right, throw in a half. And you can check that if I have this as my position, where s naught is my initial position, v is my velocity, and a is my acceleration, lo and behold, I have these nice formulas. And hence was born physics homework problems. They started with these, and then they asked all sorts of fun questions. For instance, we may say, All right, we shoot a rubber band. Oftentimes they're bullets, but I don't like bullets, so we'll do rubber bands. That's nicer, more gentle. They still hurt, but doesn't leave a permanent scar. All right, we shoot a rubber band. It goes 16 feet up in the air. What was the velocity? Or in particular, what was the initial velocity? Because the velocity will change as it goes up and down. So we can start to answer these questions now. Where does calculus come in? Well, calculus basically came in from seeing how these functions relate, but also it comes in by helping build up our intuition about how we answer this question. So we think about it for a second. We say, okay, well, what does this kind of function look like? S0 plus v naught t minus half gt squared. When we have these numbers floating around, but in the end, what does it look like? It looks like a parabola facing down. So we make some initial assumptions. We might as well just assume that S0 equals 0. Since we don't have any other information, it just makes it simple. So it tells us that if I look at time, the height does something like this. It's an upside down parabola. And what I know is I know that the maximum height here is 16. Okay, so we start thinking about that and we say, well, what happens? What's special about that point on that curve? What is different from that point compared to any other point in terms of these functions, a of t, v of t, s of t? Yeah. Well, there's always acceleration. Acceleration is always happening. It's always present. But it's not acceleration, but you're close. What's happening is there's no velocity. So initially what's happening is you shoot, your velocity, you have some positive velocity, so you're going up, but then acceleration is starting to pull you back down, so you're slowing down, you're slowing down, you're slowing down, and then at your peak, your velocity is 0. And then what's going to happen is now gravity is going to start pulling you down, and your velocity is getting bigger and bigger, but now your velocity is negative, so that's what you're heading towards the ground. So here the important thing, this is our intuition from calculus, is that at the top, or at the peak, the velocity is 0. Okay, well that's good. We can use that information. So that tells us that this time right here, let's call it capital T. At capital T, we have that the velocity of capital T is 0. Or, if you like, v0 minus g capital T is 0. And then I can solve for capital T. Capital T is v0 over g. So now I know, in terms of my initial velocity and in terms of gravity, I know exactly when I'll be at the highest point. But we still haven't answered the question. What was our question? Well, our question was, what was v0? We still haven't figured that out yet. Because we don't know this time. Okay, so how do we figure that out? Well, what can we use? Well, what haven't we used yet? We haven't done anything with the 16. This 16 hasn't shown up. All we've used is the fact that at the top the velocity is 0. So I want to use this fact now. The 16 deals with position. So now I'm going to use this because that's where 16 shows up. It's the position function. And so what do we have? We have that 16 is our S naught, which we said is 0, plus V naught of this capital T. So I'm going to replace that by V naught of V naught over G minus 1/2 G V naught over G squared. So what I did was I took the time when I knew I was going to be at the peak, and I plugged it into position, and I knew that at that time my height was 16. So we get 16 is V naught squared over G minus 1/2, and then if you multiply this out, you get a V naught squared on top. You get a G squared on the denominator, but you also have another G here, so you get, again, V naught squared over G. So if you combine these, lo and behold, you get a nice formula. Now we're really close because we know g. G is this universal constant. In this case, because we talked about 16 feet, we used the one that involves feet. So g is 32 feet per second squared. So I can rearrange this. So this says that 32 times g is v naught squared. But g again is 32. So 32 times 32 equals v naught squared. So what is v naught? Oops. Well, it's the square root of 32 squared, which is 32. And then units will be feet per second. Right. So for those of you who've had physics before, this might seem very familiar. And essentially, it's the same kind of thing you did before, but now we have our calculus intuition helping to explain how things work. All right. Okay, so let's jump ahead and talk about what we want to talk about today. So the reason that we have all these rules is to take the derivatives, we have this limit definition where we have the limit as h goes to 0, f of x plus h minus f of x over h, and we evaluate that limit. Well, that gets annoying to do as your functions get more complicated. And we want to avoid doing that whenever possible. So the way that we avoid doing that is we write down rules, and then we use the rules to take derivatives. And of course, the rules come from the limit definition. So we're sort of basically hiding the limits in the background. All right. So there's two basic things we have to do. We have to find rules for the derivatives of our basic building blocks, which here are some examples of our basic building blocks, x to the power, and rules for combining. So today we're going to do another rule similar to this, where we find a rule for a basic function. So our goal today is trigonometric functions. And in particular, I want to take the derivative of sine, cosine, tangent, secant, those guys. So let's start with the derivative of sine x. So how would we take the derivative of sine x? Well, we use the definition. So according to the definition, this is the limit as h goes to 0 of sine of x plus h minus sine of x over h. I apologize for those in the back. My handwriting is getting kind of small here. Okay, so that's what we have to find. So we think about what do we need to take this limit. Well, one thing we need to do is figure out how to deal with this sine of x plus h expression. That's okay. Trigonometry comes to our rescue because they have all these fun facts. One of the fun facts is that sine of a plus b, for two angles, that's sine a cosine b plus cosine a sine b. So I can just use that fact from trigonometry. This is the limit as h goes to 0. Then this becomes sine x cosine h plus cosine x sine h minus sine x all over h. So far I've used the definition of the limit and some trigonometry. Nothing fancy. Now what I'm going to do is I'm just going to rearrange terms. In particular, notice that these two pieces both have sine x in them. So I'm going to put them together. So when I put them together, I get the limit as h goes to 0. Sine x, well, that's common. Let me just factor that out. Cosine h minus 1 over h. So that takes care of these two pieces, plus cosine x sine h over h. Okay. So we had definition of limit. We did some trigonometry. And then we just did some algebraic manipulation. Now we look at these two pieces. I can think of this as really two things here. For example, here's cosine x. Here's sine h over h. And sine h over h looks familiar. It seems like we did something with it in the past. And lo and behold, we're in luck. We know the limit as h goes to 0. Sine h over h is 1. So this is good news. This doesn't involve h at all. So what is going to happen to this as h goes to 0? Well, it's a constant, right? It's a constant called I should say it's a constant with respect to h, because it doesn't change as h changes. So as h goes to 0, it goes to whatever that constant is. In this case, that constant is called cosine x. What does this go to as h goes to 0? 1. So this piece will go to cosine x. Okay, so this goes to cosine x. Similarly, what happens to sine x as h goes to 0? Sine x, very good. Woohoo! Yes, because it's a constant with respect to h. There's no h in there. So now the only thing that we don't understand is this piece. Cosine h minus 1 over h. Now, some of you might recognize it. I don't think it was an assigned problem in the book. Let's figure that out really quick. So what is the limit as h goes to 0, cosine h minus 1 over h? Well, we can do something similar to before. We say, all right, look, we know sine h over h. Let's try really hard to make it look like sine h over h, because if I can do that, then I don't have to work hard. So how can I make cosine h minus 1 transform like a beautiful butterfly into sine h? Well, there's not that many things available to us. What are the three techniques that we generally do? We have rewrite, which usually involves factoring, or expanding. We have trig identities. Well, there's definitely trigonometry in here. But we also have something called multiplying by the conjugate. Now, cosine, I don't know how to write cosine in terms of sine, but I do know how to write cosine squared in terms of sine. So what I'm going to do is I'm going to multiply top and bottom by this cosine h plus 1. Oh, I just remembered. Huh. There's actually a function called cosh. This is cosine of h. I should be careful here, so people don't think I'm writing cosh. Fun story about cosh. You've seen it all the time, but you've never realized it. But anyways, another story for another day. All right, so this is the limit as h goes to 0. On the top, cosine squared h minus 1, because that's what you do when you have these conjugates, a squared minus b squared. On the bottom, you get h times cosine h plus 1. And what's nice about the top? Cosine squared minus 1. It's almost sine squared. It's not quite sine squared. It's negative sine squared. Because remember that cosine squared plus sine squared is 1. So if you were to rearrange this equation, it's the limit as h goes to 0 of negative sine squared, which I'm going to write as negative sine times sine. And on the bottom I have h, and I have cosine h plus 1. All right. So really our trick to figure out this limit was to get a sine h over h, and we have it. That's good. What happens to this part? Goes to 1. The negative stays there, so we have a negative. What happens to sine h over cosine h plus 1? Well, plug in h equals 0. Sine of 0 over cosine of 0 plus 1 tells us that this part goes to 0. So the whole limit is 0. Okay, so to recap, this goes to sine, this goes to 0. This goes to cosine, this goes to 1. Put it all together, and you get cosine. All right. Woohoo! Now we have another fun function we can take a derivative of. So the derivative of sine is cosine. So now, let's try to take the derivative of cosine. Probably it's going to be something similar. So let's just go through and change things. So the derivative of cosine of x plus h minus cosine of x. Now our next step, so if we think about what we did last time, we had this nice trig rule for breaking up sine of x plus h. Well, we also have a trig rule for breaking up cosine of x plus h. So cosine of a plus b is cosine of a, cosine of b, minus sine a, sine b. So there's a negative sign involved here. So cosine x, cosine h, minus sine x, sine h, minus cosine x. So I use the limit definition. I use trigonometry. What's our next step? So our next step was just to rearrange. So here, I want to group the cosines together. So if I group cosines together, I get cosine x times cosine of h minus 1 over h, because I have the cosine h. And then I can think of this as cosine of x times 1. Okay? So that's the cosine x terms. Then I have a minus sine of x, sine of h over h. Now we just do the same thing we just did a minute ago. What happens to cosine as h goes to 0? This cosine of x as h goes to 0. It goes to cosine of x because there's no h. It's a constant. You know, we look at it and say, well, wait a second, cosine of x is a function. But remember, we're looking at how h is changing. Cosine of x is not changing. It's just a fixed value. So just think of it as a number. What happens to the cosine h minus 1 over h term? Goes to 0. Same thing as happened before. Sine of x goes to sine of x. It's a constant. And don't forget there's a minus here. And sine of h over h goes to 1. So in the end, what do we have? Well, that's 0 minus sine x. So the derivative of cosine is negative sine. And now we have these nice two simple rules. The derivative of sine is cosine. The derivative of cosine is the negative sign. So this negative here throws a lot of students off. So just remember which one goes with which. All right, so now we've taken the derivative of sine and cosine, but we have other trigonometric functions that we might be interested in. So what's another trigonometric function that we might be interested in? Tangent. All right, tangent's a great one. So how do we take the derivative of tangent? Well, I could try to do the same thing as before, but I'm going to say, wait a second. I already have my building blocks, sine and cosine. And I know that tangent I can build out of these building blocks. Namely, I know that tangent of x is the same as sine over cosine, or sine x over cosine x. So once we have our building blocks and we have our rules for how we can combine our building blocks together, it's oftentimes just faster to use these rules. So instead of going through and saying the limit as h goes to 0, blah, 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 I'm confused, we're going to skip all that and say, well, look, we know the derivative of sines and cosines, and we know how to do rules for combining them together. In this case, what rule do we need? Quotient. And how do we know? Because it's a quotient, it's division. So this says you take the derivative of the top function, the derivative of sine, well, we look it up, cosine, times the bottom function, which is cosine, minus the top function, sine, times the derivative of the bottom function. Now, what's the derivative of cosine? It's the negative sign. Divided that by the bottom function squared. Now notice what happens on the top. You get cosine squared x plus sine squared x. Because you get, minus sine times a minus sine is a plus sine squared. Over in the bottom, you get cosine squared. Now what's another way to say cosine squared plus sine squared? It's 1. Because that's like the coolest trig identity. If you only learn one trig identity, it's the cosine squared plus sine squared is 1. Okay, so I'm just going to erase that and write this as 1. Okay, so that's correct. Now we have the derivative of tangent. But usually we like to write it in a slightly different way. We say, well, look, there is a function that looks like 1 over cosine. Which function is that? Secant, right? Yeah, exactly, secant. So 1 over cosine squared is really the same as secant squared. And that's how we usually write the derivative of tangent. So the derivative of tangent of x is going to be secant squared of x. Okay, well, yeah, there's another trig function, by the way, secant x. All right, what is the derivative of secant of x? Well, again, I don't want to go back to my limit definition if I don't have to, because usually that's a lot more work than I need to do. I can think about, how do I build secant? Well, secant is 1 over cosine. That's what we just said at the very end, that 1 over cosine is secant. Okay, so if I know the derivative of secant, if I know the derivative of 1 over cosine, well, what rule do I use? Well, there's a couple rules, but essentially I can think of it as a quotient rule, where the top function is just the constant 1. So what I do is I take the derivative of the top. What's the derivative of 1? It's 0. Times the bottom minus the top times the derivative of the bottom. What's the derivative of cosine? We have it right here. Yeah, negative sign. And you divide that by the bottom function, cosine x squared. Or if you like that, sine x over cosine squared of x. Now to rewrite this, what we often do is we say, well, look, cosine squared x, that's really just the same as saying cosine of x times cosine of x. Yeah, that's true. Then we say, well, look, I can think of this as really two pieces. I can think of this part as tangent, and I can think of this part, put a 1 there, secant. So usually the way we write it is secant x, tangent x. You can also write it tangent of x, secant x, whichever way you remember it. So the derivative of secant of x is secant x, tangent x. Now when it comes to trigonometric functions, these are the 4 stars. These are the ones whose derivatives you should memorize. They're the ones that actually are useful for doing stuff. Now there are other trigonometric functions. Namely, there's 2 other ones. Let me just write them down. The proofs are the exact same here. The derivative of cotangent of x is negative cosecant squared of x. And it's the same proof. You start with cotangent is cosine of x over sine of x. And you go through and you work it out. And then you'll see what happens is essentially the signs change. You get a sine squared on the bottom. So you end up with negative cosecant squared. Similarly, you get the derivative of cosecant of x is minus cosecant cotangent. Okay. And again, same kind of argument that you did for the derivative of secant of x. So now we've added to our arsenal. So now you don't just have to take derivatives of x to the power. We can take derivatives now of things that involve sines and cosines. Let's see. All right, we can just write some problems up here. Okay, so what do? Well, it's the exact same as before. The only difference that we've really done is just add more functions that we can take derivatives of. So we shouldn't be intimidated now. We're going to have the exact same kind of problems and use the exact same technique. So for instance, if I say find the tangent line, at theta equals pi over 4 to y equals theta sine theta, what are we going to do? Well, first off, we're going to complain that these numbers are going to be ugly, but that's okay. That's life. And the second thing we're going to do is we're just going to do the exact same things that we've done before. So how do you find the tangent line? Yeah, we need to find the point that we're going to be working with, and we need to find the slope. Okay, now we know the theta is pi over 4. This is essentially thinking of theta as your x-coordinate. So our point is going to be pi over 4. Then the y-coordinate is I just plug pi over 4 into this function. Pi over 4 times sine of pi over 4. And the sine of pi over 4? Yeah. This is the square root of 2 over 2. So pi over 4. Hopefully you should know this one for the test. It might be useful. In fact, it will be useful to know that for the test. Multiply together, you get pi root 2 over 8. But it's just a number. Just don't be intimidated by these numbers. Treat it like a 5. All right, so now we have a point. What else do we need? We need our slope. How do you find out our slope? Derivative. So let's find our derivative. So y prime. So what rule are we going to use? We're going to use the product rule, right? Because what do we have? We have two functions, theta and sine theta, and they're multiplying together. So whenever you see two functions multiplying together, we're always going to use the product rule. Okay, so we take the derivative of the first function, theta. Well, if I take the derivative of that with respect to theta, that's just simply 1. And it times the function sine of theta. Plus theta times the derivative of sine theta. What's the derivative of sine theta? Cosine theta. And now I plug in pi fourths. So my slope is going to be, I'll just call it y prime of pi fourths. So that's sine of pi fourths plus pi fourths times cosine of pi fourths. And we know what these numbers are. They're square root of 2 over 2 for sine of pi fourths, and also for cosine of pi fourths. So square root of 2 over 2 plus pi square root of 2 over 8. So here's my slope. Here's my point. Now, am I done? No, because I wasn't asked to find the point and slope. I was asked to find the tangent line. So make sure you always finish your question, and then you stop. These were stepping stones to finding our tangent line. So remember, in general, we have this nice y equals f of a plus f prime of a times x minus a. This is our equation for our tangent line. This is good to know, by the way, if you haven't memorized it. There's other ways to write this expression. So just remember something, memorize something you'll remember. That's important. So I'm just going to plug stuff in. F of a is pi root 2 over 8 plus f prime of a square root of 2 over 2 plus pi root 2 over 8 times x minus pi over 4. Lo and behold. Now, if we wanted to, we can simplify this. What happens when we simplify it? Silence is not the correct answer. Well, what happens if you multiply these two together? You'll see you'll get pi root 2 over 8, which cancels with that guy. So you do get a little bit of simplification, not much. You get root 2 over 2 plus pi root 2 over 8 times x. Then this cancels with that. So what you're left with is pi squared root 2 over 32. See, these are wonderful numbers. Isn't it? It's great. We're no longer, 5, 3. Now you get these pi squared root 2s. Unfortunately, we haven't learned sine and cosine yet for the test. All right, so we'll talk a little bit more about this next week. So let's just stop for today so you can have more time to study for Friday. So I have office hours this afternoon, and I have office hours Friday morning before the test. Make sure you study. If you have questions, talk to your TAs. Make sure you're asking lots of questions in section.